Okay, today we're going to talk about the second half of our discussion on nuclear medicine. Not nuclear medicine, but nuclear chemistry. And this part, we're going to finish up our lectures for chemistry. And I'm not as sure whether we'll have anything else that we're talking about after this one. I haven't decided whether I'll have any more lectures after this one. So today we're talking about the second half of our nuclear chemistry, and the first thing I want to discuss with you is transmutation. Nuclear transmutation, and I'm going to see how well my aim is here from a perspective of, it looks pretty good actually. Nuclear transmutation is the conversion of one nuclide to another nuclide. And all of the more modern nuclides that are available, most of the heavier nuclides in the periodic table are artificially made. Most of the elements beyond uranium and polonium are artificially made by the process of transmutation. A reaction that results in the change of one nuclei into another is called a transmutation reaction. And the most common man-made device that is responsible for transmutation reactions is called a particle accelerator. And what a particle accelerator does is it uses various physical forces, magnetic forces, electrical forces, to accelerate, thus the name accelerator, particles at high speeds in order to generate and then slam those high-speed particles into nuclide such that it's transformed into another nuclide. This picture is the example of one such collider that basically takes a particle and wraps it around in a circular motion until it reaches a certain speed, and then it slams that particle or those particles into a parent nuclide with the idea of producing another nuclide. Now, transmutation reaction can essentially be divided into two types. One is called nuclear fission, one is called nuclear fusion. And it's just like you would think. Nuclear fission is the division of one large nuclide into two smaller daughter nuclides. Fusion is the combining of two small nuclides into a larger nuclide. So nuclear fission is the process of breaking apart a large nucleus into smaller pieces. So what we have is pictured here is a process where you take a high-speed, high-energy neutron. It smacks into uranium-235, and for this to work, it actually has to be uranium-235 and not uranium-238. And for a moment, you have uranium-236. The neutron remains embedded, but it's unstable and ultimately breaks apart into two smaller nuclides, krypton-92 and barium-141. It is usually the case that you start out with a very large nucleus that breaks into two not necessarily equal smaller pieces. And then there's usually some leftover or subsequent neutrons that are also produced, and there's also always energy that's produced in this process. Now, as it turns out, nuclear fission does not always produce just the bottom reaction here, which is what I showed you in the last, but it produces a series of related reactions, this just being the most common. You see that you also have technetium-137, cesium-137, I don't know what La is, and xenon-144. But what generally happens is you end up with one isotope that's about this size, 85 to 105, and another isotope that's in this range. Now this may be the most common product, and notice that all these produce some number of neutrons left over. This may be the most common product, but you always have the vast majority of products being in these two areas, or these two peaks. Now, a material that can not only perform one fission reaction, but can produce neutrons that will subsequently produce more fission products is called fissile or fissionable material. That is, it will not only participate in the first reaction, but it will produce or support this chain reaction of products where in each case you have a series of neutrons produced that go on to attack other U-235 that go on to attack other U-235 down the pipe. So the key to this production of a chain reaction is the production of these high energy neutrons in addition to the daughter nuclei that are produced. And these high energy neutrons can go on and strike other U-235 molecules and produce the chain reaction. Now, when you have a small amount of material, like here, the neutrons manage to escape the reaction area without striking another U-235. So when the mass is small enough that the neutrons can escape without striking a sufficient number of other U-235 nuclei to produce an ongoing reaction, that's called a subcritical or subcritical mass. But if you have enough mass that the neutrons cannot escape without striking other molecules and continuing the reaction, you have what's known as a critical mass. And a critical mass is a sufficient mass of fissionable material such that the reaction will become self-sustaining and continue to go on without being supplemented by outside neutrons. So section A here shows the subcritical mass, where the fissile material is too small and allows too many neutrons to escape without striking U-235 nuclei. But the other diagram shows a mass that's sufficient to allow for the continued reaction of neutrons with other U-235 molecules. Now, in addition to these production of neutrons in small daughter nuclei, the other thing that occurs is the production of a huge amount of energy. And these are actually two different types of nuclear devices that explode, or nuclear bombs. The top one is probably the earliest one, and it consisted of two masses of uranium-235. And these two masses were in separate parts of the bomb. They were kept apart, and then a conventional explosion occurred when the bomb was dropped. This forced these two subcritical masses of material together, creating a critical mass. Once the critical mass was created, then you had a self-sustaining chain reaction and a nuclear explosion. The second device was made out of plutonium. The plutonium device consisted of a sphere that was hollow in the middle, of plutonium. It was then surrounded, so you had a sphere of plutonium, which was hollow in the middle. And by being hollow and in a spherical shape, you would have a subcritical amount in contact. This was then surrounded geometrically by explosives. The explosives would cause this sphere to collapse on itself and create the concentration of plutonium in the center necessary to reach critical mass and lead to the nuclear explosion. Now actually, if you've seen movies about this, this is the type of device that's usually shown. It's usually shown as a spherical round ball-like object in the middle that around this ball is conventional explosives which will cause the ball to collapse on itself and create the critical mass necessary to cause a nuclear explosion. Now, in addition to using the energy for the purposes of creating a weapon of mass destruction, you can also use the energy for the purposes of creating useful energy. And a device that's created for the purposes of making useful energy is called a nuclear reactor. A nuclear reactor has fissile material. This material is allowed to undergo a chain reaction, and this chain reaction is controlled, and the energy is used to heat water and produce steam, and the steam then drives turbines. And here you have the steam generators here, which are generated through the heat produced. Then this goes into the turbines, which are turned and produce electricity. And then the steam then circulates back through and is reheated, and the process continues that way. Now, in order to control this reaction, you have to be able to control the fuel. The fuel is generally some kind of fissile isotope. One such isotope is uranium-235. It has to be present in sufficient quantities to allow for self-sustaining chain reactions. Now, the purity of the uranium-235 that's used for this compared to used for weapons is different. And that's why they talk about weapons-grade uranium and weapons-grade plutonium. Now, in the fuel part, which I'll show you a better picture of the fuel in just a minute. Here's the core right here. You have another substance mixed in, which is called a nuclear moderator. And the purpose of the nuclear moderator is to slow the neutrons such that it can slow down and cause a decrease in the fission. And so the moderator is put in here in order to control the degree to which this chain reaction goes on. Now let's take a closer look at this core where the energy is produced. It looks something like this. What you have are fuel cells, and these fuel cells are mixed with something called control rods. And these together are interchanged in such a way to try to control the rate of the nuclear reaction. And so on the outside, you have this coolant that goes through. The coolant enters and is heated. It's usually water. It's heated and then brought out, and then this is what drives the turbines and produces the electricity. So this is the source of the heat, is the nuclear fuel in this core, and it is carried away by the reactor coolant. Now, in a coal-fired reactor, this is just a coal furnace that heats the water. And these control rods contain the moderating material, and they're interjected between the fuel rods to allow controlling of the nuclear reaction and preventing it from getting out of hand. So it shows a nuclear core, and the core is a mix of the fuel and control rods to allow for a controlled nuclear reaction and the production of energy in that way. Now sometimes things get out of hand, and this is on the left here is a picture of 3 Mile Island 30 years after 3 Mile Island had its meltdown. And you'll notice they call it a meltdown. What is a meltdown? Well, what happens is a combination of a loss of the coolant necessary to keep the reactor cooler and a problem with the control rods, and the nuclear core becomes overheated and melts outside of its containing structure. And then you have a leakage or a breach of the nuclear material beyond where it's supposed to be. And this nuclear breach leads to a contamination of the surrounding area. There was a movie called The China Syndrome, which essentially created a fantastic scenario where a nuclear chain reaction got out of its containment and basically began to burn its way through the earth, through the center of the earth. Not something that's likely to occur. But when this contamination occurs, you have to come in and remove this waste, and that's what this guy is doing over here. But you have a huge area of contamination, and basically you have to evacuate a zone, a fairly large zone, because of the danger of the fallout, and areas around there receiving a huge amount of radiation. So this is what can happen if the material gets out of control or outside of its containment. Now, the other transmutation reaction is called nuclear fusion. Now, in theory, nuclear fusion is what everybody wants. The holy grail of this energy production is something called cold fusion, because the fusion reactions I'm going to show you have only been achievable in very high temperatures and very high pressure temperature conditions, which are very, very difficult to produce and make it not feasible on a regular basis to produce energy in this way. But fusion is where you take light nuclei, and I'll show you a reaction in just a minute, and you cause them to come together and they produce a larger mass, and this production leads to the production of a large amount of energy. A fusion reactor is a reactor that would do this, and there are fusion reactors available, but because of the conditions necessary to make this happen, they are very uncommon. And here's an example of the reaction. You have two isotopes of hydrogen which are combined together to produce normal helium and neutrons. And this is the other major advantage of a fusion reaction. If we could do it at standard types of conditions, is that the byproducts of the reaction are something normal that could escape into the atmosphere and not be a pollutant, whereas the byproducts of fission reactions are in and of themselves nuclear contaminants and have to be buried or stored in some protective way. And this is one of the reasons that fission reactions are much more problematic than fusion reactions. But to date, there's been nobody's been able to do fusion in conditions that can be readily reproduced on a mass basis. With that, let's move now to some various uses of radioactive isotopes. This is a fellow that's getting ready to undergo a stress test. And this is when we use a radioactive isotope as a tracer. Now, radioactive isotopes have the same chemical properties as their stable byproducts. In other words, radioactive iodine has the same chemical properties as non-radioactive iodine, and radioactive glucose has the same chemical properties as non-radioactive glucose. And so if you can put a radioactive isotope on a material that's used by the body in some metabolic way, you have what's known as a radioactive tracer. Now, it's a tracer when you use it to detect something. As I'll show in a minute, if you use higher doses, it can actually be therapeutic. This is a situation where they use thallium. Thallium is selected because it has a very short half-life and is gone in not 30 or 40, well, not that quickly, about 2 hours after it's given to a patient. And it is taken up by metabolically active muscle. And so what is done with this test is the patient is given an injection of thallium, and they're asked to walk on a treadmill. Now, if they are normal, then their entire cardiac silhouette will be taken up by the thallium in equal amounts, and it will look like a picture of the heart. However, if there's an area of their heart that's not perfused properly, then the thallium doesn't reach that part of the heart. It reaches the rest of the heart, and so there's an area that is deficient of thallium, and it'll show up on the picture as a picture of the heart with a piece missing. Then you allow the patient to sit and rest, and that missing piece will fill in as the blood flow reconstitutes. And so this is a way of determining whether someone has a vascular defect involving a part of the heart. I've actually had this test before, and mine was normal. It's a way of determining if a symptom that you're having is due to something wrong with your heart or something else. Now, radioactive isotopes can also be used at higher doses as a treatment. So, for example, what you have on the right here is a scan of the thyroid, and this is one lobe of the thyroid, this is the other lobe. And so you can use a lower dose and just picture the thyroid, and if you use a higher dose, the same tracer will treat the thyroid with radiation. And that's what this says. This is a technetium scan. More commonly, what's used is an iodine scan, and the iodine is selectively taken up by the thyroid. And if the person has, say, thyroid cancer, it will treat their cancer. In this case, they were treating Graves' disease. The image on the left, the picture on the left, is how these things are made, where they mix radioactive tracer with the material and put it through a column such that it is collected and used as a tracer. Now, this is a more standard radiation treatment. This is a cobalt-60 gamma knife radiation. We had a radiation treatment like this. And the way this works is you have external sources. Each of these little apertures contains an external source of gamma radiation. And the geometry is such that they can calculate exactly how much shielding to put here to allow a certain amount of the gamma radiation to go through. And then this gamma radiation will penetrate to a certain distance and lead to the destruction of a tumor. And it's called a gamma knife because it's gamma rays, and it acts like a surgical excision of the tumor. This person is probably getting a pituitary treatment because right in the middle of their head there is where the pituitary gland would be, and you can see that all these rays are sort of in a three-dimensional way are directed right at the middle of the person's head, and it actually goes in 360 degrees, and the depth of penetration is based on the amount of shielding that's put on the patient. And it's directed in such a way as to try to minimize the exposure of normal tissue to the radiation. A cobalt-60 actually undergoes 2 degradations, and in each degradation the gamma emissions are used to produce or used as radiation treatment or radiation therapy. Now, in addition to treating people and treating tumors, and in addition to using these scans in order to image certain parts of the body, radiation can also be used to disinfect or preserve food, and that's this, where radiation, ultraviolet radiation, various types of ionizing radiation can be used to kill bacteria, or it can be used because it can penetrate certain materials. It can be used to image inside bags in order to examine baggage for weapons before the person gets on the airplane. Another use for radiation is a smoke detector. And what happens is you have a small chamber over here. It's the ionization chamber here. This is an enlarged portion of this ionization chamber. And what you can see is you have 2 plates. One plate is negatively charged, one is positively charged. This is generated from this battery. You have a source of alpha particles from the americium, and these alpha particles will cause an ionization of this atmospheric molecules here, and they move this way based on whether they are negative or positively charged. If smoke enters this, it causes the particles to not become ionized as they would normally be ionized, and prevents this flow of electrons, and this triggers the alarm, and so that's how the smoke is detected. Radiation has many biological effects. This is a direct biological effect of radiation. And by that I mean the radiation itself can damage DNA. It can take normal cell, damage the DNA, causing a mutation of the DNA, producing a tumor cell. This tumor cell then expands and produces a tumor, which is why people who are exposed to radiation sometimes develop cancer. Now, radiation, the radiation source here can be one of 2 types. It can be non-ionizing, which means that when it strikes this cell, it doesn't have the ability to cause damage to the DNA. And anything less energetic than UV radiation is like that. So visible light, infrared radiation, microwaves, etc. Now, while microwaves can cause damage, they do not ionize DNA. They cause damage in other ways. So they don't interact with biological molecules. But now, higher energy radiation interacts with biological molecules. It's called, and it causes an ionization of things like DNA, and this ionization leads to damage and can lead to the development of cancer. So the radiation causes biological harm to systems that are vulnerable, and these vulnerable systems, or particularly the DNA, can lead to the development of tumor cells and tumors. This table sort of shows you where energy in the radiation reaches the point that it can cause ionization. And it's right about here where the division between visible light and ultraviolet light is where the damage begins to occur. So anything less than visible light in terms of energy, in terms of frequency, anything longer, broadcast waves, radio waves, microwaves, etc., infrared waves, all of these do not cause ionizing radiation, do not cause damage to the DNA or to other biological molecules. But now over here, you have the various types of electromagnetic radiation that are associated with DNA damage, and they are the ones that are associated with cancer risk. So you have UV light, tanning booths, sunlight, incidence of melanoma and skin cancer. You have X-rays with the development of sarcomas and leukemias related to X-rays, and then you have gamma rays. And so these are the ones you have to be protected from to prevent the development of cancers. Some of these can burn you and can cause problems for other reasons, but are not the same as this group over here. Now remember that as the energy increases, the ability to cause this kind of damage increases. And as the energy increases, the frequency increases and the wavelength decreases. And so that's how you keep track of which of these can cause those kinds of problems and which can't. Radiation, we've been speaking about the direct effect of radiation, which is the direct impact of a radiation on a biological molecule such as DNA that causes this energy hits this molecule, causing a loss of an electron and ionizing the DNA directly. The radiation can also strike water. The water loses an electron and becomes ionized. It interacts with other water molecules, producing oxidized molecules, which then interact with biological molecules and damage indirectly. So this is an indirect effect of the radiation on the biological molecules, and this is the direct effect. The direct effect is related more often. It's uncommon, but when it occurs, it's uncommon, but when it occurs, it can lead to tumors and cancers. This is much more common. When it occurs, it generally leads to things such as aging, and the production of oxidizing radicals is what leads to aging, and these are the sorts of oxidizing radicals that occur that can cause that problem. This is why the much more common injury that occurs in people who are in tanning booths and spend a lot of time in the sun is wrinkling of the skin, as opposed to the actual development of skin cancers. This is more related to that wrinkling process, and this is related to the tumor development process. Now, the various types of radiation that are produced have various abilities to penetrate through materials. The larger the molecule is, one thing to remember is the larger molecules do not penetrate very far. The other thing is if it has a higher energy, it will penetrate farther. So if you look at this, from top to bottom here is deeper and deeper penetration through materials. So you start with the alpha, it can't even make it through a piece of paper. A beta will go through a piece of paper, will also go through human tissue, but is stopped by metal. Neutrons will pass through the first three here, but is stopped by water. And then gamma rays will go through just about anything except lead shielding. Now this is a problem that has become much more evident in the last, I'd say, 15 or 20 years, and that is the seepage of radon into homes and other buildings. And where that comes from is you have rocks in the environment that contain uranium-238, And uranium-238, when it breaks down, as you can see down here, it breaks down to radium-226 and ultimately radium-222. And radium-222 is what enters into the home through cracks in the foundation and so forth. And if it reaches a certain level, it becomes risky or dangerous to the people inside. And this radium can actually cause, it's a alpha emitter, and it can actually cause problems with the development of lung cancer, particularly in people, if there's enough of it around that you inhale it into your lungs, it can cause problems with the development of tumors. And so when you buy a house, you usually get a radon test, and they put a thing in your house to see how much radon is in your house. And if it reaches a certain level, then you have to do certain things to try to decrease the radon in your home, or else you'll have a hard time selling your house. So the radon, this is, when people talk doing a radon test, this is what they're talking about. Now these are three pictures of three different kinds of radiation detectors. Well, when radiation is detected, how is it measured? Well, one way to measure it is a unit called a becquerel. A becquerel is 1 disintegration per second. Now if you think about that, 1 disintegration per second is not a lot. And so they had to develop some other unit that was much greater than a becquerel to sort of evaluate radiation as it really occurs in nature. And it was named after Madame Curie. A Curie of radiation is 3.7 times 10 to the 10th disintegrations per second. So it's a hugely larger number than a becquerel. This unit of Curies is what we use when we talk about treating people and exposing people to radiation. So we'll talk about giving so many microcuries or so many millicuries of radiation to treat a thyroid cancer or something of that nature. And this is what we're talking about. Then you also have the absorbed radiation, or the rad, and this is a unit of energy per kilogram of tissue. So 1 rad is 0.01 joules of energy per kilogram of tissue. And so we talk about, when we measure these things, we can measure them in terms of the disintegrations per second, and we can also measure it in terms of the energy absorbed in the tissue. And the various detectors are shown across the top. The old-fashioned Geiger counter, a nuclear scintillator, which causes a photo type change that can be detected by a light detector, and then a dosimeter, which can be used to measure radiation at various levels or doses. Now this shows another way in which radiation is detected. And what we do is we put a badge on people that changes color after it's exposed to a certain amount of radiation. And again, it's RADS, radiation absorbed dose, or gray, which is another term for radiation absorbed dose. Now, in terms of the damage that is caused, and this is different depending on what tissue we're talking about. The Seaford is a measure of tissue damage, but there's a different amount of tissue damage depending on whether you're radiating muscle versus brain versus lung versus bone marrow, because each is more or less sensitive to the damage that occurs. And the Seaford is also converted into something called a REM, or Röntgen equivalent for man. And this is the unit that you most frequently will hear about when you talk about the damage that can occur in people by the exposure to radiation. They'll talk about, you're allowed so many rem or millirem of radiation exposure. And this is based on standard models that show what certain amount of damage that can occur. The other way in which radiation is measured is based on its relative biological effectiveness, and this is much more difficult to assess, and that's why it says approximate measure. It's because it's relative to some standard, and those standards are not necessarily equally sensitive to the radiation damage that's done. So there are different units that are used to measure the emission of radiation by a radiation source, but what's important is what's absorbed from the source by the biological individual, and the damage that occurs because of that absorbed dose. And what you'll notice is that people that work around radiation will get behind lead screens in order to minimize their radiation dose that they're exposed to. And my last slide just gives you some idea of the various radiation exposures depending on where you are or what you're doing. Just as a background, this 620 is what's considered the usual exposure to the average individual in the United States, 620 millirem. This 5,000 is the amount of REM, the allowable amount of annual REM exposure that's allowed to someone who works around nuclear material. So that's the limit. This is the amount of REM someone's exposed to if they are given a CAT scan, a whole body CAT scan. So you see that if you get 5 CAT scans in a year's time, you've reached the same maximum allowable dose that they allow nuclear workers. And I can tell you that patients who need to be treated get many more CAT scans than 5 CAT scans in a year. Some of them have 10 or 20 CAT scans in a year's time. And you can see these other types, these various types. So, this ends this talk, and I'm still trying to decide whether or not I want to have any future talks. And hopefully, I will say that since we didn't have anything in the way of calculations, that the quiz will probably be more fill in the blank and multiple choice than anything else.